Hey guys, and welcome back to another session on efficient Python. In this session, we're taking a look at decks, or you can call them DQs, whatever you like. I think the general consensus is that they're called decks, and yeah, that's fine. Now, these are a really interesting data type. They come from the collections module, so they're built in, nothing to install, nothing to worry about on that front. And what makes these really interesting is it's not entirely obvious when you first look at them, but behind the scenes, this implements as a doubly linked list. So if you've done a bit of computer science or that kind of leak codey kind of stuff, you might be familiar with this. But the main point is that these are really fast in doing append or pop operations from either side. To highlight this, I'm going to quickly flick over to the Python docs and just show you a time complexity chart of a list first. Now, here's our list here. This is from the wiki-python.org. I'll stick the link to this in the description as well. And the ones I want to draw your attention to, so we look at append, and that's fine. It's constant time, and that's okay. However, when we look at insert here, this assumes an O of n. And O of n basically means, so say for example you had a list of 5 items, n in this case is going to be 5. That's effectively 5 operations just to insert one item at the beginning. You know, this n is always going to be proportional to how big your list is. So to put something at the beginning is an O of n operation. Suppose you then want to pop an item. Popping from the very end is constant time, and that's fine. However, this pop intermediate O of n, so assume you're popping from the very front of the list. You want to take an item out from the front and return it. That again is O of n. So, you know, adding to the end or removing from the end, that's fine. That's nice and quick. But as soon as you want to kind of put things into the beginning or take things out of the beginning, then it's a whole other story that becomes really, really slow. However, if I scroll down to our queue here, so to collections.deque, which I've imported, a double-ended queue, effectively. Check out the difference. Append, O of 1, constant time. Append left, so the same as like insert of index 1. So the same as index 0, constant time as well. Pop, constant time, same as the list, but pop left, O of 1. So basically it's saying, if you want to add something to the left or to the right, it's going to take the same amount of time regardless. Same as popping, if you want to pop from the end or pop from the start, it doesn't matter. It's going to be the same amount of time, and that's what makes these such efficient data structures. So in this video, I'm going to show you through a quick example of kind of popping from the left, appending to the both sides as well. And then I want to look at building a fancy text editor where we're going to use the deque to basically handle some undo operations for us. Right then, let's get into it. So I've got deque imported from collections, and the first thing we're going to do is just create an empty deque. So I'm just going to do DE, short for deque, and just do this here. Now the first thing I always do when working with a new data type is examine it using the dir function. This is built in. Effectively, it tells you all of the attributes and methods of an object. So in this case, we're passing my deque to the dir function. So if I run python3 main.py, I can go ahead and see the different things I can do here. So a bit like a list, you know, we can see append. Append left is here. It might just be cut off by the screen. We've also got pop and pop left as well. So those are the ones of interest that we're going to be looking at. I'm also going to take a look at the max len. So I'm going to write that here just for a second. And I'm also interested in rotation as well, which is pretty cool. So let's start off with max len, and then we'll dig into an example of the append left, pop, and pop left as well. So just quickly get this cleared here. Let's just do a quick example. If I said 1, 2, 3, so convert this list into a deque, and then do max len equal to 3 here. All right. So we're basically saying this deque can only, you know, it can't go over this length of 3, as you know, might sound obvious. So we print de. We hit run, and now let's just try and do de.append of 4. Let's just see what happens. Now that's really interesting. Of course, it's as you expect, it stayed the same size, but look what happened. It's removed that initial 1 here, and then it's then put the 4 onto the end. So as you can imagine, you know, as these objects come in, I suppose we had 1, 2, 3. If we then have a new one coming in here, this 4's coming in, what basically happens is all the items shift down, the 2 and the 3 go here, and then the 4 just then sits at the end. And then suppose we have 5 come in, same thing. You know, the 3 would be moved to the front here, the 4 would go here, and then your 5 would then sit like that. So say if I now was to run de.append of 5, we would expect to see this situation here, 3, 4, and 5. So let's quickly tidy this up. de.append of 5, And there we go, 3, 4, 5. Nice. Whilst we're here, let me quickly remove this. And I want to show you what a rotation does as well. If I'm honest, I don't tend to use rotations a whole amount of the time. But, you know, it's one of those things we can do. It's an interesting method. We may as well show it. Python 3 main.py, yeah, de rotative 2. So that's kind of done the rotation that we just saw. So if we did a 1, for example, yeah, there we go. So basically everything's now been shifted forward by that degree. So the 1 has moved forward 1, the 2 has moved to the end, the 3 has gone back. It's basically equivalent to saying pop this from the end and insert it back at the beginning here. So let's take a look at some nice append and append left methods. I'm going to allow this, as I now have a max len of 8, make it a bit bigger. And this is kind of where things come and be quite interesting. So if I do de.append, we'll append a string, and then we'll then run a similar command underneath with append left, and we'll append the Boolean value of false here. So it's, you know, if you're familiar with lists, this should be pretty, well, yeah, pretty familiar, I suppose. You're appending, that's, you know, that's taken from the list. We see that method, same method here. The append left, you know, looks pretty similar, except of course we are going to then append to the other side. And there we go. So let's break that down. We started with 1, 2, 3. We appended to the right, you know, as normal as you would do with a list, and that hello is now gone in here. The append left, you know, that's kind of similar to how you might, you know, for a list, you might do something like insert 0 and then your item. That's effectively equivalent, except the difference is this guy here is pretty naughty. That's in O of n time. That's, you know, it's going to shift all the elements down. That's not good. This append left here, that is super fast. That is in constant time. So if you're after some kind of structure where adding things to the left and to the right are equally as important, I suppose if your list is really big as well, you should definitely use a deque, because appending to the left is a constant time operation. It's nice and fast. You know, they're basically equal speeds to do. So I'd definitely recommend using them. Okay, so for the popping left and right, I've just done a bit of a different DQ, so a different deque, I should say. Sorry, I fall into that trap all the time of calling it a DQ. I think it's because of how it's spelled. But yeah, some people do call these DQs. I try to call them deques. Try being the main word there. Sometimes I do call them DQs, but yeah, that's fine. So de.pop. So again, similar. If you're familiar with lists, this will look pretty similar. So if we run that, we can see the E is gone. This also does return. Let's just call this pop last here. This also does return the item. So if I do de and then pop last, there we go, like that. No, not del. De. There. That's better. There. So yeah, this bit here, that is my representation of the deque, A, B, C, D. Because we've done pop, the E has been popped off the end here, and that's also been returned to this. So that pop last has been printed, and there's the E there. Now let's do one from the other side. And again, I'd like to highlight this. This is something where if you were to like try and remove from the front of the list, in a normal list, you're looking at O of n. You know, so not ideal. It's proportional to how big the whole list is. Yeah, so not good, especially if you've got like a really big long list and it's running all the time. So pop first, but all I need to do here is change this to POP left, like that there. So popping from the left-hand side, again, both the same time complexity, popping from the right as default, popping from the left, of course, that's unique to the deque. And we'll clear that before we run it, shall we? Make it a bit more obvious as to what we're doing. And there we go. So we're basically left with the B, C, D in the middle here. The A has been removed by pop left. That's been made clear there. And this bit has happened there. And then let's see what we've got here. Yeah, D.pop, that pop last, and yeah, we can see that here. So in my view, those are the methods of interest. You know, you can do, there's a few more things you can do with it. Let's just do DE one more time. But to be honest, if you're familiar with lists, a lot of these will probably make a lot of sense. For example, we've got copy and count. You can do those with a list. We've got remove, we've got reverse, index, you know, so we've got all of the basics are going to be there. One more thing that I suppose is of interest is this extend left. So that will exhibit the same kind of behavior as append left. You know, it's just the kind of reverse version of extend, which again you can do with a normal list. So what I want to show now is kind of a nice working example of this. I want to bring up some code, which is basically a funky version of a text editor. So I'll clear the screen, we'll bring this code up and then we'll run through how that's implemented. So I've got a basic class defined here called text editor. I'll quickly run through this and then I'm going to try and explain why a deque is a decent option for this use case. We've got a text attribute here and this undo history attribute, and this is my deck here. Now, I've done this as a max len of 5, and this will be really important in just a minute's time. And the whole point of this class really is to be like a simple text editor with an undo function. So I have an insert text method. This takes in something called new text, and it simply concatenates this onto self.text here. So over time, this is basically going to make this grow. So our self.text attribute is going to be growing as this method is being called. Now, each time a user passes in some new text, we're also adding that into our deck here. So notice how we define this as a max len of 5. So each time, someone adds in some new text, we're basically appending the state of this text into this undo history thing here. And the reason why I've done this as a max len of 5 is because we don't want this undo to kind of go mental and just be absolutely gigantic. So this could be whatever number you want, but in this case here, we're taking advantage of the fact that we can append quickly with a deck, and also we can pass this max len of 5 here to say, let's only keep track of the last n operations, so to speak. And then my undo function here, this is making use of the deck's fast ability to pop stuff off the end. We'll quickly break this down. So in this case here, suppose we have some history already, so some stuff's been inserted. We first pop off the end, which is faster than a list, which is good, and we then say our text is equal to the last thing that we kept in history. This elif is to take care of the fact that if there's just one thing to pop, then we can just revert it back to an empty string. And this else is just to catch any edge cases where there's nothing, so we print nothing to undo. And I'm going to do this by adding a couple of bits. I want to print off the state of the text attribute and this undo history attribute each time. So I'll go ahead and try that. And then underneath, let's print off the status of the text and the undo history. Let's give that a run. Okay, there we go. So we can see, in this case here, my text just has hello, and my deck also has hello in as well. Let's go ahead and do a couple more. So let's bring this guy underneath, and we'll change this to world without any space. It's fine for now. In fact, yeah, let's do a space here. We'll keep it nice and fancy, just so it makes it a bit more readable. Okay, there we go. So our text is now hello world, and our deck now has hello, and our newest state, hello world here. Let's do one more, and then we'll try a pop operation. I'm being lazy, so I've just done the first thing that's come to mind. Let's do Python. All right. We'll clear the screen, and we'll hit run on this guy. See what we've got. Okay, so our text has now grown to hello world Python. Our deck is now holding 3 items. The first state, the second state, and this hello world Python here. Let me just show you something. If I made this to 2, clear the screen and rerun, see how it's now, because of this max len being equal to 2 here, which is unique to the deck. Look what it's done. So this was hello world, and then when it comes to this guy here, this hello world Python, that initial hello is now dropped from our deck here. So this is kind of a nice way of maintaining, guess how sustainable this is. If you're working with kind of large batches of text, and this is a big number, the more of your RAM you're occupying. So keep this fairly small size, and you should be good to go. So up next, we'll try and undo. So we'll do editor.undo, and then let's bring this guy. So we'll just kind of bring up the big reveal, so to speak. And just to kind of make things a bit clearer, we'll do a new line break here. So we'll do the 3 print statements after those insert texts. We'll do the undo, and then we'll print off the text after the undo and the state of the history after the undo. Right, there we go. Let's bring that up. Okay, so we can see these 3 here. So this, and this, the 3 inserts. So hello world, and then hello world Python. And of course, we can see the states kind of moving up here. Hello world, and then when we had our last one here, so our last insert was hello world Python, the deck held that state of hello world Python, and then we called undo. So let's just go through and see what happened. If the len of the history is greater than 1, yes, it is in this case. Pop off the last item. So in this case, remove this here, this hello world Python. This meaning that this is now the end of our deck here. And then we did self.text is equal to self.undo history -1. So considering that this is now the last item, we're just reverting the text back to this state here, so of hello world, and we now have our text equal to hello world. And I get like, with this being a fairly small example, it might seem trivial. You might think, well, I can use a list here. You could, and you could probably write some funky logic to, say, check the length of the list each time, and if it gets big of an X, you can slice it from the beginning. But it just makes things a bit awkward as well. And if this has been done in a large capacity, the append and pop methods are faster for a deck. And I think this is genius. I love having the ability to say keep this structure of a certain size. And that's it really. I hope this video was helpful. If you're fairly new to Python and you're new to the different modules such as collections, this is a fairly interesting one. As I said, it's not one that you're going to be using every day, but it's useful for these kind of situations where you need a structure of fixed length and you want the ability to append and pop at the same speed from both ends. Alright, cheers for watching guys, and see you all in the next session.